Today we're going to talk about linear functions in business. Linear functions appear all over the place in business, and that's because they're some of the easiest functions to deal with. Keep in mind that a linear function is uniquely defined as a line that goes through any 2 points. So if you have 2 points of observation in your business, you can then draw a line through them and use that as a linear model. Okay, so let's start by recalling some of our business terminology. We have very common total quantities of cost, revenue, and the difference between those, profit. Okay, oftentimes in business, when we want to model our cost, we will do it as a function of x, where x is the number of units. Here in all of these things, x represents the number of units or quantity produced or people served if you're in a service business, something like that. C is going to be the total cost. R is going to be our total revenue. And profit, remember profit is defined as the difference of the revenue minus the cost. That's going to be our total profit. And keep in mind that profit can be negative and will be negative when your costs exceed your revenue. Your revenue is not really going to be negative, your costs aren't really going to be negative, but the difference between them can often be negative if you're losing out and you're not making in enough revenue to cover your costs. Okay? So these you may have already seen, but now I'm going to introduce to you some new quantities which I will refer to as the marginal quantities. Okay, and each one of these total quantities has a corresponding marginal quantity. So corresponding to cost is MC, the marginal cost. MR, that's going to be the marginal revenue. And MP, and that's going to be your marginal profit. The word marginal here refers to the change in the total quantities as we increase our number of units by 1. So that is to say, as X increases by 1, the total quantities change, I should say increase, by approximately their corresponding marginal values at that number of X. Okay? A lot of times simply you can think of the marginal quantities as how much more of this am I getting when my production or sales or whatever increases by 1 unit. So let's go over that concept, and I'll just speak it out instead of writing it for each one of these functions. And again, we're going to see these functions as being functions of x, where x is the number of units. Okay, so I rewrote them over here as functions of x. Okay, so marginal cost, that's going to be approximately how much do my costs change, how much is my total cost changing when I'm producing just 1 extra unit. Marginal revenue, how much additional total revenue am I going to bring in when I increase the number of items or units that I sell by 1. And then finally, marginal profit is how much are my profits overall going to increase as I increase the number of units by 1. Okay? So these are just totally general concepts here, and you don't see the linear form here right now, but this lecture is on linear functions in business. So now let's put some linear functions on there, and that's going to be some of your most common types of functions. And I'll show you guys how you can translate the linear form into words, and how you can translate or find the marginal quantities that correspond to each one of these linear forms. Okay, so let's say we have some sort of business, maybe we're making books or something like that, and we have a cost function, maybe that's going to be 400 plus, 5x. Now, do you guys remember the components of the total cost function? There's 2 different components representing different things. The fixed component here with no x dependence represents my fixed costs. So that means that I have to pay $400 per month or per week or whatever my time unit is, and that's my cost for renting the building or renting the equipment or the hiring of people to work for me. And then this is the variable cost over here. You can see it's variable because it is multiplied by the variable x. And the number next to that variable x represents how much it costs to actually produce the units, like how much is actually the materials costing me. So you can see that if I'm a book factory or something, it costs me $400 to rent the space or rent the printing press, and then it's going to cost me $5 per item produced. So $5 a book produced. Okay, so let's pretend we're still in the book business here, and now we're going to talk about our revenue, where we're going to sell the books, and let's say we sell them for $25 each. And revenue always has that familiar form of the per unit price multiplied by the number of units, okay? So do you know how much we're selling the books for each book? That's right, $25 per book times how many books did we sell, and that's going to be our total revenue. Okay, so why don't you guys take a minute to practice writing down and simplifying the functional form of the profit function here. So pause the video and form for me a simplified expression of the profit function. Okay, so let's check and see what you did. The profit is going to be revenue minus cost. And when you're computing this profit function, please always be careful to surround the entire cost function with an outer parentheses. If you do not do that, then you run the risk of not factoring this negative sign through, and then your answer is going to be incorrect. So the simplified form you should have got here is going to be 20x minus 400. Okay, so now you can see how these quantities might be represented linearly for a business example. And then we're going to go over to our marginal quantities, the marginal cost, marginal revenue, marginal profit. When your total function is linear, and by total function I mean any of those total quantities of revenue, cost, or profit, when total functions are linear, the corresponding marginal functions are always equal to the slope. The slopes of the total quantities. Now, as you move on in your study of mathematics related to business, you will find that for arbitrarily defined total quantities here, the corresponding marginal quantities are going to be defined as the derivative of the functional form here. So you might not know what a derivative is yet, but stay tuned for that. And keep in mind that as we talk about linear functions, the derivative of a linear function is always its slope. It's the constant coefficient that multiplies the x. So here, when the total functions are linear, the marginal functions are always going to be fixed. They're going to be equal to the slopes of the total functions. Okay? So to see if you understand that, why don't you just take a minute to pause the video and write down what you think I'm going to write for MC, MR, and MP given these functional forms here. Okay, so I just have to recognize the slope portion of each one of these linear functions. So for MC, that's 5. MR, that's going to be the 25, and for the MP, that's going to be 20. And so now I won't write it down on the board, but I'll just discuss what each one of these things translates to. Because remember, marginal quantities is the amount that the total quantity is going to change when I increase my unit value by 1, when I increase the x value by 1. Okay, so marginal cost, it costs me $5 for each additional book that I'm going to produce. My marginal revenue, I'm going to make $25 additional for every extra book that I sell. And marginal profit, well, because I sold it for $25 but it cost me $5 to make, I'm going to get $20 in profit for each additional unit of X, each additional book that I sell. So that's what the marginal quantities mean in general. Okay? Do you guys remember what the break-even point is? Break-even point. That's something that was referred to for the profit there. The break-even point is when the profit is equal to 0. That's when your revenue, your incoming money exactly matches your cost, the money that it costs you, and so that's when your profit is 0 or when R is equal to C. Okay, so now what I'm going to do is I'm going to take these linear functions here and I'm going to illustrate what the break-even point looks like on a graph when we graph the two quantities of the revenue and the cost. Okay, so let's say that we have one set of axes right here. Here's X number of units, and let's assume that all these total quantities are going to be in units of dollars. What I'm going to do is I'm going to graph the revenue in blue. I'm going to graph the cost in red. And you can see that these are both linear functions, and when they're equal, that was the break-even point, is actually corresponding to solving both of these things at the same time, simultaneously. So that's going to be the place where the two lines intersect. So R of X, you can see that its y-intercept is 0 and it has a slope of 25. C of X, its y-intercept is 400 and it has a much lower slope. It has a slope of 4. So this is 400 plus, sorry, it has a slope of 5. And you can see that the red line and the blue line here intersecting right here at this point here, and that's going to correspond to the place where R is equal to C, and that's our break-even point. Okay, because that's our break-even point, and both of these functions are always upward, their slopes are upward because it's going to always cost you positive money to make an extra item. It's always going to make you positive money to sell an extra item. So we know the slopes are always both going to be going up. So on either side of this, now we can consider if this is our break-even point, this is the place where the profit equals 0. Now we've broken the plane into two regions. One leads to positive profit and one leads to negative profit. Okay, so let's put this in green because it's good to get positive profit. Here's our break-even point, the intersection between the 2 points. If we sell any amount greater than that, that leads to positive profit. And that's really what we want. The P is greater than 0. And on the other side of the coin, if we didn't make and sell enough items to reach our break-even point, this is going to be the region of negative profit over here. And you can see that's negative because the C, which I'm subtracting off here in the profit, the C is above the blue line, the R, and so these are the places, all the places over here are going to be where I'm not making enough money and I'm actually losing money on that business. So that's why the break-even point is so important, to know where you stand and what your goal has to be, at least to break even. Okay, so linear functions, very applicable to the total quantities that businesses are familiar with, but another very good place to use linear functions in business is when we're trying to set the price. You can see that the revenue function over there is found by multiplying the price times the quantity. And how do we know what we should set our price at? There's this whole other theory, maybe you guys have heard of it before, it's called the theory of supply and demand. Have you ever heard of that? Maybe in a class on economics or something like that. So now we're going to look at how linear functions show up in the theory of supply and demand. Okay, and then each one of these has a law for it. We have the law of demand, and then we have the law of supply. Now, demand, that's on the consumer end of things. Like if I'm the one who's actually consuming it, purchasing it, and I'm going shopping for something. The law of demand simply states that if the price is lower, I'm going to want it more. Okay? So for both of these things, we have to define our variables. P is going to be the price, and Q is going to be the quantity. Okay? And if the price is lower, the law of demand says, then if the price is lower, the quantity demanded will be higher. If price is lowered, then the quantity demanded is higher. Of course. If you're going to make the price cheaper, I'm going to want it even more. However, inside business, there are two sides of the coin. There are the people who are demanding and the people who are supplying. And the law of supply has the opposite statement, which is to say that if I'm the one supplying it, if the market price is higher, then I'm going to want to supply more of that thing. So that's the opposite here. If the price is lower, the demanders will demand more. But on the other side, if the price is raised, the quantity supplied increases. So that's what makes sense for the supplier side of things. And we want to really look at both of these at once on some sort of axes. And this is a little bit confusing now because I don't have an X anymore. I'm going to have a Q for quantity instead of an X, and that's just like what's commonly used in the literature, so we're going to be consistent with that. So where I usually have the X-axis, I'm going to put a Q, and then over here I'm going to graph the price, and I'm going to graph each one of these in a different color. I'm going to graph the demand in red, and I'm going to graph the supply function in blue. And oftentimes these two functions are both stated as linear functions, so the quantity or the price as a function of quantity is linear, okay? Now, on the demand side of things, I'm going to want more if the price is less. So what does that mean? If I was going to be a line, do you think the slope of this red line for the demand is going to be positive slope or negative slope? That's right, it's going to be a negative slope because if the price goes down, I'm going to want even more. And keep in mind that this isn't going to hold forever because eventually you can see this is going to go through the Q intercept right here. When the price is 0, I would probably want even more than that. But it usually holds for some certain region of quantity that makes sense for your problem. If the price goes down, I'm going to want more quantity of it. That's what the demanders say, and the suppliers say the opposite thing, which is to say that, hey, if I see that market price rise, that makes me think for my business I want to supply more of that thing. So if the price goes up, now I'm going to supply even more of it. Okay, so when the price increases as I'm a supplier, I would like to make more of that. So this is the supplier side of things, and this is the demand. This is the supply here, and this is the demand. Now each one of these things has its own equation, so I'll write it in blue. P is equal to MQ plus B. That's going to be for the supply one in red. And then demand is going to have its own linear equation. P is equal to MQ plus B, where here the red M and the blue M would probably be different values. Keep in mind the supplier slope is always positive, and the demander slope is always negative. And when you guys see this, whether you're in a class on economics or business calculus or whatever, if you see a chart where it's been graphed supply and demand and you don't know which one is which, just think of it this way. D for demand and D for down. Demand is always going down. The slope of that line is always negative because demanders will demand more when the price decreases. Okay, so if you see two lines on a graph and you know one has to be supply and one has to be demand, demand is the one that's going down, supply is the one that's going up. They're not necessarily always linear, but commonly they are, and so you can see a linear example here. Okay, so seeing two lines intersect in the plane reminds me of our theory of the solving out systems of linear equations, and you can see that there's one unique value right here where both of those equations are equal, and that's what we're going to call the market equilibrium. According to the theory of supply and demand, the market is going to just work itself out. The price is going to rise and fall accordingly. Things will go on sale at the store, or the suppliers will make more or lower their supply chain somehow, their price. Things are just going to work out naturally so that the price gets set at this market equilibrium quantity. Here, since this is on the Q-axis, this is the market equilibrium quantity. And over here, since this is on the p-axis, this is going to be the market equilibrium price. So you can see that the market equilibrium has two values. It has a value for quantity, we'll write as Q, a value for price, Q comma P, and that's usually what we're going to look for. If we've been given some sort of functions to go with those red and blue lines there, then we will look for the place that they intersect, and that is the predicted natural price and quantity at which the market's going to settle in. Okay, so let's get a concrete example here so we can kind of see how to find the market equilibrium. I'm going to give you a couple equations. We'll talk about what the numbers mean, and then we'll use algebra to solve out for the market equilibrium. Okay, so let's say, for example, the supply function, the supply pricing function, and I'll continue to write that one in blue because I'm using blue for supply here. Let's say that's P is equal to 10 plus 2Q. Okay, and then we're going to have a demand function. Demand pricing function is going to be in red there. Let's say that that is P is equal to 50 minus 2Q. Okay, we have two different lines, and keep in mind that if you saw two equations that relate P and Q, and they said which one is the supply equation, which one is the demand equation, if they're linear equations, again, you're just going to go back to this hint. What's the slope? Is the slope positive or is it negative? Because I know that demand goes down when price is a function of quantity. So that means the slope on demand is always less than 0. The slope on the supply function is always going to be greater than 0 there. So even if I didn't write these black words here telling you which was which, you should be able to recognize which is supply and which is demand just by looking at the sign values for the slopes. Okay? So let's find the market equilibrium. And we want to find the market equilibrium by solving these two equations simultaneously. So you saw some examples of how to solve things simultaneously by the process of elimination or substitution. Here, actually this is the easiest situation to be in because this one solved exactly for P. P equals something. This one solved exactly for P. P equals something. So if you want them to be the same at the same time, you simply have to set them equal to each other and forget about the P's altogether. Okay, if you want to think about that in terms of the process of substitution, I'm just taking this for P and I'm putting that value over here, and so I just get this one statement, which is one equation and one unknown. So I'm going to bring this to the other side here and get 4Q. Bringing that to the other side, I'm going to get 40, and solving that for Q, I get Q is equal to 10. And then I go over here and look, the market equilibrium quantity, if that was my example right there, let's say that would be the quantity of 10. Okay? So that's the perfect medium for the market where the supplier wants to supply 10. The demand out there in the market is that people want to buy about 10. And what price are they buying it at? Now, if you're the supplier, you really care what the price is because your revenue function will be formed by multiplying the price times the quantity. So what amount of revenue, what amount of profit can I expect to get out of this? I also need to know the market equilibrium price. Does anybody know how to get that from this equation here? That's right, you can just plug it back in. So you just take the Q is equal to 10 here, and if these are truly both equal at the same time, the price should be equal. Let's check. 10 plus 2 times 10, that's 30. Okay, this one, 50 minus 2 times 10, that's 30. Perfect. So the market equilibrium price right here is located at exactly $30. Okay, 10 units selling for $30 a piece. That's what the situation the market likes to be in. Okay, we have a couple more things to discuss here, which is like, what if the price at the store isn't 30 right now? What if the market price is 20? Or what if the market price is 40? What if we're at a different price, which is not the equilibrium price? Then the quantity demanded and the quantity supplied will not be equal if the price is not located at the market equilibrium price. And then we're falling into a category of either a surplus or a shortage. Okay, so let me tell you a little bit about each one of those things there. You may have heard that before, especially you may have heard about the surplus. If you've ever been to a store that calls itself like a surplus store, that's when the suppliers have supplied too many. The demanders didn't want that many at the market price, and so then they have a surplus. Usually that stuff ends up at the Ross and I can get it for half price, right? So I like that case. I like the case of where I'm going to be in a surplus. That means we have more items were supplied than demanded. That means we have too many. Okay? And then the other side of that is that if we're not in a surplus, then we're in a shortage, or sometimes it's called a shortfall. Those mean the same thing, and that's the opposite of a surplus, which is to say that more items were demanded than supplied. The trickiest part of this example here is for you to locate regions in this plane where we either have a surplus or we have a shortage. Okay? So just like before when I showed you profit and I showed you a region of positive profit and a region of negative profit, why don't you go ahead and challenge yourself, pause the video, try to find the region of surplus and the region of shortage here. Okay, so let's figure this out. Let's see. More items in the surplus are supplied than are demanded. And remember that our supply function here, supply was in blue. So that is to say that maybe if I was up here at, let's say, the number $40 per item, then the supplier will have supplied this many, but the demanders really didn't like that price point. They only demanded this many. So I will have more quantity supplied here than demanded over here. And so everything that's above the market equilibrium is going to be a region of surplus. Okay? So this is a little bit different than what we saw for positive and negative profit. Positive and negative profit was separated by a break-even point on the right and left. The places where we're going to have a surplus or a shortage, those are speaking about the number of items. So those are going to be separated with a horizontal line instead of a vertical line. So if our price point is above the market equilibrium price, then we're going to end up supplying more than we're demanding, so everything up here is a surplus. And then at the same token, we have the shortage area down here, where let's say that our price was just a little less, it was $20 there. If our price was that low, then the suppliers didn't want to supply that many, but the demanders really liked that price, so they were demanding a lot. So then the demanders demanded more than were supplied, and so that's the shortage region here. You have to think about this a little bit backwards than how you usually think, because when you fix a price, let's do the price of 20. When you fix a price, remember blue is for blue is for supply here. You will see what price you have and then go down to the Q, the quantity axis, and then you will see that this is the number that are supplied because I used the blue line to go down. Okay, and then at that same price point, at the same $20, I'll go over here and I'll wait until my horizontal $20 line intersects the red line. The red is for demand, and I'll see that wherever that is on the Q-axis, that's the number that's going to be demanded. Okay, so whenever more items are demanded than supplied, that's when I get a shortage. So you're kind of looking at this on a number line. Okay, so when you fix a price over here, you're fixing yourself on a horizontal line. Then you have to see where that intersects both of those functions, and you have to go down to the number line on Q and see what's greater, the number demanded, the number supplied, or at the market equilibrium quantity. That will be where they're both even. So that's the equilibrium. Okay, so before we close this out, let me just take these statements of these equations and I'll show you that I can prove algebraically that at a price point of $20 here, that I have a shortage, okay? When the price is equal to $20, let's see the supply. I'll write that again in blue. How many are supplied? I have to plug it into this equation and solve it for my Q, quantity supplied. So $20 is equal to 10 plus 2Q. 10 is equal to 2Q. Q is equal to 5, and that is the number of items supplied. 5 items are supplied at that price value. Then how many are demanded? Because I need to compare those two numbers to determine whether I have a shortage or a surplus. $20 is equal to 50 minus 2Q. So then minus 30 is equal to minus 2Q. So then Q is equal to 15, and that in red, those are demanded. Okay? So if you see a question which is asking you at this fixed price point, do you have a surplus or do you have a shortage or a shortfall? You have to use both equations to solve out for both values of Q and ask yourself which value of Q is larger. Here, more are demanded by the market than are supplied, and that means we have a shortage of those items. If it was the other way around, where more are supplied than demanded, then we would have a surplus, and then usually that stuff has to get dumped off at the surplus store. Okay, so hopefully you have a better understanding now of how these price functions can be modeled with linear functions.